Okay, all right. Okay, well, happy Wednesday. Today we'll take a look at k-nearest neighbors as a classification algorithm. Give me some time to get your midterms graded. I haven't met together with my TAs and graders to do it. We'll probably do that sometime next week, and to get everything graded. And I'll be traveling. So I will be traveling on Friday and Monday. So Friday and Monday's lectures will be pre-recorded, and then probably the earliest I can do the grading will be like Tuesday of next week or something. And so so just ask for your patience in getting everything graded there. Okay, let's talk about k-nearest neighbors. So k-nearest neighbors, the way it works is you have training data. The training data, it's a little bit of a there's no training phase in KNN, k-nearest neighbors. Basically, you just have data that you're going to use to help you make future predictions and things like that. Okay, all of your training data comes in and they are labeled with a class. So we're assuming you have kind of generally like numeric values as your x, and your output is a categorical variable. Okay, and this is basically how the algorithm works. You measure the distance from your test case to every single other point in the training data. Okay, the distance is usually Euclidean distance, but you can use other distance metrics. And then yes, you have to measure the distance to every single other point in the training data. That can be very computationally expensive if you have lots of data points in your training data. But anyway, that's the first step. And then once you've measured that distance, you sort the resulting distances. Okay, and then based on that, you are going to select the k observations with the smallest distance. Okay, and so the k observations with the smallest distance from your test point, those are your nearest neighbors. Those are your k nearest neighbors, hence the name. And then, and basically every observation in that group of k, they get a vote as far as like which class something belongs to. And then whichever one has the highest votes, that is that's going to be your predicted class. So that's, we'll illustrate that. There's a few things to talk about. So depending on your data, the choice of what value k you use could influence the performance of your model. Okay, smaller values of k will lead to overfitting or high variance. Okay, so you remember you have this bias variance trade-off. Okay, so variance is the idea that if you happen to get a different random set of data, would your predictions still be the same? And if you use a small value of k, depending on your random set of data, that your predictions might vary a lot. Okay, but large values of k tend to kind of over smooth the boundary, and you end up having the opposite problem of underfitting the data. Okay, so you have low variance, but now you have high bias. So now you might have too kind of simplistic of a boundary, and so it's not able to kind of detect like the nuances between your different classes. Okay, you can use cross-validation to try to estimate the performance of the model for different values of k, but that's that. Okay, so let's just talk about some other things. Other things that could come up when you do k-nearest neighbors is you can end up with ties, okay? One recommendation is that if you only have 2 classes, then just pick an odd k, and then you don't have to worry about ties, right? So it's if it's either going to be a yes/no or an A/B type of thing, pick an odd k. You don't have to worry about ties. So you pick k5, k7, whatever. Okay. If you have an even k, or if you have more than 2 classes, like if you have 3 classes, then it's possible to have a tie among your k-nearest neighbors. So you could have 3 classes, and you might have k equal to 7, and you might get a 3, 3, 1, right? So you have 3a, 3b, and 1c, even with 7 neighbors. And so you could end up with a tie or things like that. So what do you do in that case? Well, the answer is there's no hard rule about how ties should be resolved. You have a few options. One is if there's a tie, you just designate it unclassified. You just say, well, I don't know, it's tied, so I'm not going to make a choice. The other is you can switch to the one nearest neighbor, and generally you only have one nearest neighbor. It is also possible that you have 2 observations that are the exact same distance from your test case. I would say that's very rare, especially if you have a continuous variable. Having 2 observations that are exact same distance is, probability approaches 0. But if you have a discrete variable, then stuff like that could happen. But you could switch to your one nearest neighbor and say, all right, whichever one is the one nearest neighbor, that's what we'll use. You can also just select randomly among the top tied groups. That's going to result in higher variance, though, because depending on just your random luck, you might get different choices. And then you can also, among the groups that are tied, you can then select the group with the one closest neighbor. And that's not necessarily the same as choosing the one nearest neighbor. Will often yield similar results, but it could be, again, if you have 3 classes and you have 3 of A, 3 of B, and 1 of C, with k equal to 7, it is possible that your one nearest neighbor is observation C, okay? But then you might want to say, well, if I have 3A, 3B, then I want to choose between group A and group B, and then I'll switch to the one nearest neighbor, and perhaps group A has the one nearest neighbor between A and B, okay? So that could happen as well. KNN is generally considered to be a hard classifier versus a probabilistic classifier. So things like logistic regression would be a probabilistic classifier. The Bayes classifier is also probabilistic in that it gives you a number between 0 and 1. K nearest neighbors, generally, it's a hard classifier. It's just this dot gets assigned to category A, or this dot gets assigned to category B. You generally don't get probabilities. But you can extend it to provide kind of pseudo probability outputs. And that's done by kind of considering the proportion of neighbors that belong to each class. That's like R has a KNN function, and you can ask for probabilities. And basically, it has kind of extended this. So, for example, if you use k equal to 5, and you look at your 5 nearest neighbors, if 3 of them are A and 2 are B, you would then say it's a 60% probability of A because 3 out of 5 are A or something like that, right? And if it was like 4 out of 5, then your probabilistic thing was going to be 80%. And if it's 5 out of 5, your probabilistic value would be 100%, okay? But again, that should be your first clue that these aren't really real probabilities, because anytime you get 100% probability, you should start questioning it a little bit. So, but yes, the way KNN would do a kind of a pseudo probability is say, okay, the 5 nearest neighbors for this observation are class A, therefore, you know, our kind of probability is going to be 5 out of 5, 100%. Okay, let me give you your first view quiz answer, which is the letter C. C as in cat. Okay. All right, so you have a few different distance metrics. We normally use Euclidean distance. So what is that? X, you know, the delta x squared plus delta y squared is equal to, you know, I don't know, the hypotenuse, right? So, you know, a squared plus b squared equals c squared type of thing. You use that for your Euclidean distance. In higher dimensions, it just generalizes. I would say there are other distance metrics you can use, and this might appear as options. So you have things like Manhattan distance, and then you also have Chebyshev distance. So here, maybe we'll just go to the Wikipedia page. Oh, this is not a link. Okay. What is this? Chebyshev distance. Here we go. And do we have a comparison here? Okay. So Chebyshev distance is the how do I zoom in on this picture? I can't. Okay. It's kind of like chess distance. Like if you have the king, how far can you get? That would be your Chebyshev distance. So in one move, you can go into the corners or up, down, left, right. And in 2 moves, you can get kind of two squares away. And in 3 moves, you can get 3 squares away, right? Even though, so Euclidean, this distance from here to here would be like 1.41 square root of 2. And then this would be, I don't know, more than that. 2 squared plus 2 squared. Oh, is it? Wait, no, hold on. Okay. But anyway, 2 root 2. So things like that. But Chebyshev, basically going straight versus going diagonal is going to be the same. Versus, oh, okay, here's your picture. Taxi cab is like Manhattan distance. Basically, you can either go in straight lines. So if you wanted to get in from this spot to this spot, this has a distance of 4. You got to go 1, 2, 3, 4 that way, and then 1, 2, 3, 3 that way. So it takes kind of 7. Your distance is counted as 7. Euclidean, you go the 4 squared plus 3 squared is the same as 5 squared, so that distance is measured as 5. Whereas with Chebyshev, you can just go 1, 2, 3, and then 1 over 4. So Chebyshev only has a distance of 4 or something like that as far as counting your distances. There's mathematical formulas for each of these things, but those are your things. Okay. Advantages and disadvantages of KNN. Okay, KNN is really simple, straightforward to implement. I think you, wait, did I make you do it in your homework? I think, yes, it's in your homework, right? This homework. I'm like, I know it's in the homework. Is it this one or the next one? Yeah, it's this one. So, okay, you guys have till next week. I gave you till Monday, right? Okay. Yes. Okay. All right. So, I mean, you might find that there's some parts that are annoying, but as far as like implementing KNN, it's relatively straightforward. Okay. It's non-parametric. There's no kind of assumptions about the underlying data or the distributions or anything like that. We're not assuming, things are normally distributed or anything. We just measure distances, okay? And then there's no training, which is both a disadvantage and a disadvantage. Okay, there's no training phase. So, when you do, say, neural networks or whatever, you have to kind of train your model in that you have to find what values of, your W's and your biases and things like that you got to use. Or even like linear regression. You have a training phase, which is basically determining what your slope and intercept are, right? That's the training. As far as KNN goes, there's no training. There's no trying to figure out coefficients, okay? It's just when it comes time to make a prediction, you're going to take your test case, compare it to all of the available data that you have, and you use that to make your prediction, okay? The disadvantages of KNN is that it can be very computationally expensive for large training data sets. And I would say this number one disadvantage, that it's computationally expensive for large training data sets, has really caused KNN to, I would say, fall out of favor in kind of this modern, more modern machine learning stuff, right? So, you think about machine learning, and it's still relatively new, and I would say KNN was popular in the earlier days of machine learning, but now that we're like moving towards these really huge models and huge data sets and things like that, KNN has fallen out of favor just because it can't keep up with really big data sets. Okay, and then other things is that what used to be an advantage that there was no training phase, is also a disadvantage in that it's not going to learn any kind of rule or function for classification. You're not going to get a slope and intercept value. You're not going to get anything. It's just look at this new thing. What can we say about it? We then have to kind of go through our brain or whatever and kind of compare it to every single other thing that we've ever seen. Okay. Performance also suffers when you have very high dimensional data, and then choosing what K to use isn't straightforward. It's always just kind of like guess and check and see which one has the best performance when you do cross-validation. So that's kind of our discussion on that. Okay, let's go ahead and just look at the algorithm at work, and we'll talk about that. So here I've generated some random values using RMV norm, and we're going to have values in class A and class B. Okay, I'm going to just plot two-dimensional data. KNN can be used in higher dimensions, so you could have three-dimensional data, four-dimensional data, and you're still just measuring basically Euclidean distance in 3 dimensions or something like that if you have higher dimensional data. Well, I guess the other thing is, because you are using distance metrics, you want to make sure your x variables are all on similar scales. So, kind of like lasso, you want to normalize your data so that, for example, if you have measurements, if your variables are measured, you're looking at height and weight, okay? And you're measuring height in inches and you're measuring weight in pounds, okay? Basically your shortest person and your tallest person, I don't know, your shortest person might be like 4.5, if we're talking about adults, 4 foot 6 inches or something. 54 inches would be kind of on your shorter end. And then on the tall end, I don't know, 6.5 feet or something. So what would that be? 78 inches or something. So kind of like from your lowest to your tallest, you're going to get like a range of around 24 inches or something, okay? Versus if you're talking about, lightest to heaviest in pounds, your range is going to be, much more like 250 pound range or something, okay, going from the lightest to the heaviest. And so, so if you use that, and if you use those numbers raw, then obviously the weight values will have a much more bearing on like your distance metrics. So so I guess step 0, which I didn't put in here, but your step 0 would be like scale them, you know, turn everything into z-scores, so that you're just looking at kind of how different the values are. But anyway, here I've just generated some values with XA and XB, and we're going to plot them. So I've got these dots, red dots and blue dots, okay? And we're going to put in a test case. So this is our training data that are labeled, and we'll put in a test case right here. So looking at this dot, we ask, is this, you know, in the red territory or the blue territory? Okay, what do you guys think? Okay, well, yeah, I mean, so it's a little bit of a judgment call, right? Okay, so this is what we do. We are going to measure the distance from this dot to every single other data point, okay? And that's represented by these lines here. So I've intentionally left off the code behind doing all of this because that's your homework, right? But here I'm illustrating how it's working. So we measure the distance from our dot to every single other point. And then we say, okay, if k equal to 1, what is our closest neighbor? So that is going to be this dot right here. And that's, so I've drawn a circle to represent that. This is the closest. You don't have any other points closer than this. And so if k equals 1, our one nearest neighbor is red. Therefore, this is going to get classified as red. Okay. If we go up to k equals 3, okay, these are our 3 nearest neighbors. I have 2 red and 1 blue. Okay, so 2 red versus 1, we're going to get, this is going to get voted 3. With k equal to 5, now I have 3 blue and 2 red. Okay, so this will get voted blue. So that's why it was kind of tricky for you guys to look at and figure out, is this going to be red or blue? Because your eyes are looking at this and you say, well, maybe it could be red, maybe it could be blue, because you kind of like, our eyes kind of pick up on stuff like that. So with k equal to 3, it's red. K equal to 1 is red. 3 is red. 5 is blue. If you go to 7, okay, these are your 7 nearest one. This one just is barely a little bit farther away, so it's not one of the 7 nearest neighbors, but these are your 7, and you have 4 that are blue and 3 that are red. Okay, so 4 blue, 3 red, that gets voted blue. And I think, is that it? Did I go to 9? Okay, I guess that's it. Okay, and then, you know, you can keep going, but so what is it? Red 1, 3 red, 5 blue, 7 blue. So it's a little bit, this spot could be red or blue depending on what k you choose, okay? Versus this point, would you say this is in red territory or blue territory? I think we'd feel better about saying it's in red territory, right? Okay, and yeah, when you do k nearest neighbors, let's look at, you know, our nearest neighbors. So we're going to measure the distance from this dot to every single other dot. Okay, and you might wonder, like, why do you have to measure the distance from this dot to this dot? It's obviously like this is not going to be the nearest neighbor. And the thing is, you know, in 2 dimensions, yes, we can easily see that this point down here is not the nearest neighbor because like our eyes and our brain can process 2-dimensional data really, really, really quickly, okay? However, 3-dimensional data, we can process kind of well, but you can imagine like there's some weird rotation and you actually don't know, right? Like well, we don't really see stars in Los Angeles, but I don't know, have you gone to like this space museum where they show you like, this is what the constellation looks like, but in reality, like this star is like super far away, and this star is like, I don't know, 200,000 light years away, and this one is like 10,000 light years away and stuff. And so if somehow you were able to like rotate the stars in space, it would look totally different. And, you know, you could end up having something like that. And then again, you know, in 4 or 5 dimensional data, you know, we have no way of really picturing it in our brain. And so if I asked you like, what are my nearest neighbors in this 5-dimensional data, we don't have a way to do it. Okay, we can't, there's no shortcut where we can just say, oh, let's look at these. You have to kind of measure your distance to every single other point. Okay, so yes, in 2-dimensional data, it feels silly measuring the distance to this point out here because it's very clear that all of your nearest neighbors are going to be up here. But in higher dimensions, there's no real shortcut to just quickly identifying your nearest neighbors. Yeah, question?
I saw in the previous slides that one of the disadvantages for KNN is that it's not good at working with high-dimensional data.
Yeah.
Like, why is that the case?
Why is it not great at high-dimensional data?
Yes, it's here we're trying to generalize to 2D to 3D.
Yeah. So the answer is it does work. The performance suffers in higher dimensional data because, so just imagine you have, we'll keep it simple, right? We've got red dots, we got blue dots, okay? So in 2D, like, what is the boundary between red and blue? It's gonna, generally, you have some kind of line, okay? And it might be a little bit curvy, but that's okay. All right, in 3D, what is your boundary? It's gonna be some kind of like surface, or I don't know, a manifold, is that what we would call it? It could even be like red is enclosed in some funny blob, amorphous blob thing, okay? And 4-dimensional data, okay, now you have this hyperplane, but it's not a plane, it's something weirder, okay? And as you climb into your dimensions, you need more and more data, or data, whatever, to define this quote-unquote border a little bit well, okay? And the thing is KNN actually doesn't ever actually define the border for you. You just end up kind of feeling it out with all of these test points, okay? So I think the higher dimensional stuff actually is not unique to KNN. It's something that exists in that, like, if you want to be able to distinguish between one and another, you need lots and lots of additional data points. And especially if you have like high correlation between your variables, then it gets even harder to tell what's the thing that's responsible. So for example, you know, like, what is responsible for driving up, you know, or for, you know, when you look at a house or an apartment to live in, is it the number of bedrooms or the number of bathrooms that's important? And to really figure out the difference, you would want to have a wide range of values for all of these things. And you'd want to know, like, okay, if I have very few bathrooms and very few bedrooms, it's this cost. If I have lots of bathrooms and lots of bedrooms, it's this cost. But to really figure out, like, is it the bathrooms or the bedrooms, you would also want to have a place where you have lots of bedrooms but no bathrooms, or few bathrooms. And then you'd also want to have a place with lots of bathrooms but very few bedrooms. And then you could really figure out, like, which of these things is the one responsible. But the problem is you don't find lots of bedrooms, no bathrooms, or lots of the opposite, whatever I just said. You don't find those cases very much. So is it the bathrooms or is it the bedrooms? It's hard to know which one is the one responsible, and we just say, well, it's both, because they always kind of go together. But and the same kind of stuff happens in higher dimensional data as well. So anyway, okay, so we calculate the distance. Now we want to say, all right, what's our 1 nearest neighbor? 1 nearest neighbor is red. What's our 3 nearest neighbors? We got 2 red and 1 blue, so we're also going to say this point gets classified as red. What's our 5 nearest neighbors? We have 3 red and 2 blue, so it's still red. What's our 7 nearest neighbors? We have 4 red and 3 blue, so it is still red. So we feel pretty good about this point kind of being in red zone, okay? Because at k equal to 1 and 3 and 5 and 7, it all gets classified as red. Okay, let me give you your second view quiz answer, which is the letter B. B as in bear. All right, so K&N boundary regions. So I just, on this earlier slide, what did I say? I said, oh gosh, I said, it doesn't learn any kind of rule or function for classification. And that is true. So what I'm going to try to show you here is, can we have a rule for classification that K&N won't learn directly? And the answer is yes, it's just a lot of work to figure that out. And so the way you figure out boundary regions using the K&N algorithm is that you have to just test out a whole bunch of points, figure out which ones are red, figure out which ones are blue, and you use that to draw your boundary. So I don't know, if I can show you, I don't know, can you see all these tiny little dots? Basically, I had the algorithm, right? I drew a ton of dots here, and I tested every single one. I said, for this dot, if I use k equal to 1, is it going to get classified as blue or red? And this one got classified as blue. And then I said, what about this dot right here? Is that going to get classified as blue or red? And it got classified as red. So therefore, I know the boundary between blue and red is somewhere between this dot and this dot. Okay? And so normally with K&N, and I would still argue that with K&N, you don't get to figure out where your boundaries are between red and blue, but you can kind of brute force it by just testing out a whole bunch of different locations and saying, is this one blue, or is this one red, or is this blue, or is this red? And then by figuring out, okay, this point here was blue, but this point over here was red, therefore the boundary between blue and red is right there and there, okay? Does that kind of make sense as far as how we've established these boundaries? So, so these dots are actually, I don't know if you can see it, it's the exact same dots as in this picture. So this picture, I've got these blue dots, and these are the exact same dots, I think, right? So if you can just kind of squint and you look at, this triangle of dots over here, you can see, oh yeah, that's the same triangle of dots right there. Okay, so it's the exact same dots from the previous thing, and this is the border between red and blue regions when k equal to 1. When we have k equal to 3, this ends up being the boundary. And again, the way it worked was I said, all right, is this dot red or blue? And it got classified as red. Is this dot red or blue? This got classified as blue. So I don't know, we can kind of zoom in. And I guess for this dot, our 3 nearest neighbors are going to be this, and this, I think. Our 3 nearest neighbors are these 2 blue dots and this 1 red dot, so that gets classified as blue. But then when I pull over here, I think our 3 nearest neighbors are going to be these 2 red dots and this 1 blue dot, so now that gets classified as red, okay? And something like that. So, with k equal to 5, so you can kind of see as k gets higher, the boundary gets, I don't know, simpler, smoother. I don't know if that's the right word to use, because it's still not like smooth, but it's it approaches something smoother, I guess. Okay, and you this overfits our data a little bit, right? Like this kind of is an outlier point. That's this dot feels like it shouldn't be over here. It feels like this is in the blue zone, but because of this one dot, this whole region gets now thrown into blue, okay? And as K gets higher, you can see, all right, you know what, we're not going to worry about these one-off dots that show up here and there. That's going to reclassify all this. So this all of this kind of gets classified as blue, okay? So, K equal to 5, K equal to 7. So, as K gets higher, the boundary between red and blue just kind of starts approaching basically almost like a straight line between red and blue, okay? Here's something, just a more concentrated cloud of points, all right? So we've got red, we got blue, kind of a mix of these things, and we're gonna say, all right, go ahead and draw the regions that get classified as red and classified as blue. So again, we drew a huge grid of dots, and this is with K equal to 1, and so K equal to 1 means every single dot kind of gets its own little sphere of influence. So this one blue dot out here, that's definitely kind of in the wrong territory. Like, it gets its own little, what is this called? An exclave, okay? Where it's like, created its own thing, right? And these, this little red dot out here gets its own little kind of thing. These dots out here gets its own thing. And look at that. This one dot, I don't know, whatever, something happened, okay? And its nearest neighbor is the red dot, and something like that, right? So we can see this is overfitting our data here. Okay, that's K equal to 1. With K equal to 3, a little bit less of that happening, okay? You need at least a couple dots to kind of form a thing here. Something a little bit odd happened here in that, like, we have these 3 blue dots, and so this is the sphere of influence and stuff. So that's with K equal to 3. Here it was K equal to 5. K equal to 7, and you can see going from real kind of jagged boundaries, and this isn't exactly smooth, but the shape of the boundary gets easier to explain, right? It's kind of just like, okay, draw this kind of, make a, I don't know, this boundary here, okay? K equal to 7, K equal to 9, 15, right? So at this point, I would say our boundary between red and blue territories is getting smoother and smoother. And so, these blue dots that ended up over here are definitely kind of classified in the wrong side, and these red dots that show up over here just kind of get ignored as well, okay? And as I climb up, so here it is with K equal to 21 and 31, and by the time I'm up at K equal to 31, basically the boundary is like almost just a straight vertical line that just goes up and down between our the red side and the blue side here, okay? So that's K nearest neighbors as far as classification goes, and here we've just been doing it for two classes, but again, it can be generalized to any, more classes, things like that. You can use different distance metrics, although I would say Euclidean distance probably gets used in 99% of your cases. And that's often how our brain thinks about stuff anyway. But yeah, okay. So comments, okay. I think I'm just repeating myself here. Smaller values of K can lead to overfitting. So notice the exclaves and the enclaves formed by individual points in kind of, quote, enemy territory over here. Okay. I'm just trying to, what is it? I don't remember. What's the difference between an exclave and an enclave? I don't know. And then, I don't know. You have like, all right. Okay. And then larger values of k tend to kind of over smooth the boundary. So if you look at this, basically, again, kind of like a simple straight line. So that's going to lead to underfitting your data there, okay? And then lastly, you can actually extend KNN for regression. So I've been showing KNN as a classification algorithm where we just, every dot in kind of the sphere of influence gets a vote as far as is this red or is this blue, and it's used as a classification algorithm. That's fine. It could also be used for regression, and the way it works there is, well, the first two steps are basically the same. You calculate your distance to every single other data point in your data set, and then you find your k nearest or your k closest training data points, your nearest neighbors. And then, as far as your prediction goes, is if you have a numeric response variable, you say, all right, these are my 5 nearest neighbors. This one had a response of 7, this one had a response of 8, this one had a response of 7.4, this one had a response of 9, and this one had a response of 6.2. And then you take the average of those 5 points, and you'll say, that is my prediction for this thing. So basically, you just take the average or the mean of your 5 nearest neighbors, okay? And then you can further tweak this by saying, well, I don't want to just take the mean, I want to take a weighted mean. And, this is my 1 nearest neighbor, and so it has, its value gets weighted the heaviest, and this, among the 5 nearest neighbors, this one's the farthest away, so it gets weighted the least or something. And you have different formulas as far as how to calculate the mean of these things, but basically those are going to be your primary strategies. Just take the mean of all 5, your k nearest neighbors, or do some kind of weighted mean. How you want to do your weighted mean, you can tweak it a little bit. I want to have linear weights, I want to have this square root weights or whatever. It's all the same, it's just small tweaks, and maybe one of these things give you slightly better performance than another, but not going to make a huge difference there. Okay, last view quiz answer is the letter E. E as in elephant. E is our third view quiz answer. Okay, and that will be it. We'll wrap it up here for K nearest neighbors. So Friday and Monday's lectures will be pre-recorded. And so have, I guess, a great weekend or rest of your week. We'll see. I'll see you Wednesday. All right. We'll end there. Thank you.